Okay, welcome back. Today we're going to talk about the center of mass of a system. Up until now, we have always assumed that the objects under our study could be approximated as a point particle undergoing translational motion. If we look at the diver in the first video, we can approximate this as a point particle undergoing simple translational motion. She's not moving, she's staying the same, it's just a point particle. In the second frame, however, we're seeing the additional rotational motion, what we call general motion. The important thing to note, however, is that the center of mass still always follows the same parabolic arc, which is why we can make our initial assumptions regardless. So with a bit of calculus, we can find the center of mass for virtually any object, though the derivation might be a little bit nasty and it would take a long time. All of it, however, starts with just 2 points. So in the case of what's in front of you, you have 2 points. You have a mass A and you have a mass B. There are 2 different masses. You sitting at some point over here, you know the distance here. You know the distance here. If you want to know what the center of mass distance from you is, then the equation to use is right here. Whatever your mass of A times its distance from you from the reference point, plus whatever the mass of B times its distance from you, all divided by the sum of mass A plus mass B. What that's going to give you is this distance right here, your center of mass distance from you. It's very important to note that the reference point does not matter. If it were 1 meter from the objects in question, or 1 kilometer from the objects in question, or in the case of astronomy, 1 light year from the objects in question, the math would still put the center of mass at the same relative point in space relative to the masses in question. Now you're saying 2 points, that's just too small. What if I want to add a third point? What if I want to add 300 more points? All right, well in that case, let's for simplicity add a third point out here. So we've got a third mass C. It is distance from you, x, c. So how do we modify our equation? Well, it's pretty simple. We're just going to add the mass of C times the distance between the reference point and C. And then on the bottom, we're just going to add the mass of C. And that should give us some new center mass distance. Okay, so let's hit a problem real quick. 3 people of roughly equal masses, M, on a lightweight air-filled banana boat sit along the x-axis at positions 1 meter, 5 meter, and 6 meters, measured from the left hand as shown. Find the center of mass and ignore the mass of the boat. Okay, well we'll just use that equation we just had up a moment ago, and we have x, center of mass, it's got to equal mass A, x, A plus mass B, x, B plus mass C, x, C, all divided by mass A plus mass B plus mass C. Alright, so that's the equation we have. Let's plug in some numbers. So we'll notice that all these masses are supposedly the same. They're all M. So then I'm going to end up with a M times XA plus XB plus XC divided by 3 times M. Okay, well, M divided by M, the M's can go away. So I've got XA 1.0 meters plus XB 5.0 meters plus XC 6.0 meters, all divided by 3. So I've got 12 divided by 3 would be 4.0 meters. So let's see, is this reasonable? We came up with roughly 4 meters. Now look at our masses. We have 2 people on the front end of the boat, 1 person on the back end of the boat. We wouldn't expect the center of mass to be somewhere out here. We wouldn't expect the center of mass to be somewhere out there. It's reasonable to think that the center of mass is somewhere between these two people, and because there are two on front and one in the rear, it's reasonable to assume that it should be closer to the front than the rear. So is this reasonable? Yes, it is. So yeah, it's a short video. It's a pretty straightforward concept. Please do check as you learn and complete the rest of your assignment. Thank you for watching.